today we'll look at the electric potential due to a system of spherical conductors. But first we'll look at one conductor, and recall for a conductor any excess charge is going to be distributed on the surface of that conductor. And the electric potential outside the conductor is 1 over 4 pi by the permittivity of free space multiplied by the charge over r, where r is the radial distance from some point outside the conductor to the center of that spherical conductor. So in other words, r is greater than r, where r is the radius of that conductor. Now recall that the electric field inside a conductor is 0. So recall that the electric field is minus the rate of change of the electric potential with respect to the radial distance, and therefore when the electric field is 0 inside the conductor, then the electric potential is constant. So given that the electric potential is 1 over 4 pi epsilon naught by q on r, well, on the surface, r is equal to r, and inside that conductor, the electric potential must be equal to this electric potential. So it stays constant inside the conductor. So basically outside the spherical shell or solid, the electric potential due to this spherical body is the same as that of a point charge with a magnitude of q. Now suppose we have a system of spherical conductors connected by a wire. So this has a radius of r1 and this one has a radius of r2. Well, the charge is going to start to flow to this conductor, because remember that excess charge wants to get as far away from each other as possible because they have the same sign of the charge. And these charges continue to distribute on the connected spheres until electrostatic conditions are met. And this occurs when both spheres are at the same potential. So in other words, the potential is equal to V1, which is equal to V2. Okay, so in the same way that we had excess charge distributed on one spherical conductor, and we're under electrostatic conditions, the sphere is an equipotential, well, this system now can be treated as a single conductor with the same potential. And we neglect the charge distributed on this wire relative to the charge on the spheres. So the electric field on the surface of sphere 1 can be written as 1 over 4 pi epsilon naught by the charge on sphere 1 over r1 squared. And similarly, for sphere 2, we have a similar electric field, except the charge magnitude is q2 over r2 squared. And given that both spheres are equipotentials, so they're at equal potentials, so for sphere 1, we can write 1 over 4 pi epsilon naught by q1 on r, and similarly for sphere 2, we have a similar result with a different charge magnitude and a different radius. So from these two equations, we can see that the electric potential is equal to E1 by R1, and from these two equations, we have the electric potential is E2 by R2. So therefore, E2 is equal to R1 on R2 by E1. So if the radius of this first conductor is greater than the radius of this second conductor, then the electric field of the second conductor is stronger because there's more charge per unit area distributed on this sphere. So in other words, sphere 2 has a higher charge density. And I'll see you in the next video.